Okay, so one of the final topics that has to do with drawing Lewis structures and VSEPR theory is the expanded octets. So in the SL syllabus, we mostly look at molecules and polyatomic ions that follow the octet rule, where atoms share electrons in such a way that they feel like they have full outer shells, usually 8 valence electrons. And we also look at some exceptions where molecules have incomplete octets, where they bond and they have less than their full octets of electrons. So this kind of goes in the other direction, and we see molecules and polyatomic ions that will end up sharing electrons in such a way that they have more than 8 electrons. Now, the reason why this is possible, it kind of goes back to, it goes back to electron configurations and also hybridization. This is an HL topic, by the way. So this will only start happening with elements that are in period 3, so the third row of the periodic table, because those elements have a 3s that's generally full. If they're nonmetals, it will be full. And then they've got the 3p level that can have up to 6 electrons in it. And then they've also got a 3d level. And that 3d level may be empty, but it is relatively close in energy to the 3p. And so through the concept of hybridization, it becomes possible for not only s and p orbitals to combine, but also to pull in some d orbitals and combine them all to make hybrid orbitals. And so when we combined an s orbital with a p orbital, then we called it sp. And then when we combined it with 2, we called it sp2. And when we combined it with 3, we called it sp3. And we had 2 domains and 3 domains and 4 domains. Well, although it's beyond the syllabus, if you combine s with 3 p's and a d orbital, you get a type of hybrid orbital called sp3d. And then if you keep going, you get sp3d2. And those are the hybridizations for 5 and 6 electron domains, which we're going to see in this video. So you don't get asked to explain how this is possible or why this is possible, but I'd like to give at least a little brief explanation of how this is possible. So it just has to do with the fact that 3d orbitals can also be involved in hybridization and can therefore be involved in locations for sharing electron pairs. So we won't see this for any elements that are in period 2 or period 1. So they're never going to have expanded octets, but we will see this with elements starting in the third period. Okay, let's get into some examples. So some of them are fairly obvious. If you see PCl5, now if we normally draw P and we think about its Lewis structures, we would expect P to make 3 bonds because it has those 3 unpaired electrons. But it does have 5 valence electrons. So if we see one where phosphorus is bonded to 5 things, now clearly you can't make 5 bonds without going beyond 8 electrons, because 5 bonds will contain 10 electrons. So if we're trying to draw an expanded octet for PCl5, my normal approach, or my recommendation, is draw the central atom, and it's pretty clear P phosphorus is the central atom here because there's only one of it. And chlorine, as having 7 valence electrons, is more likely to make just 1 bond, so I'm assuming those are around the outside. Well, if each chlorine makes 1 bond, I'm just going to assume that every one of these valence electrons of phosphorus is going to get shared to a chlorine atom. For the sake of time, I'm just going to represent lone pairs, non-bonding pairs with these lines. Usually I think dots are a bit better, but we can often get away with just those lines too to represent pairs. So this is an accepted Lewis structure. This earns you a mark for the Lewis structure of PCl5. The phosphorus atom, the central atom, has what they call as an expanded octet. It's not really an octet, it's beyond an octet. So it has 10 electrons around itself. So I know that kind of hurts your octet mentality to do that, but PCl5 does exist, and it's just our job to draw how the bonding might work. We can do the same thing with SF6. As soon as we see that 6, we know that there's definitely more than 8 electrons, because 6 bonds is going to be 12 electrons. So I put the sulfur in the middle, and I draw its 6 valence electrons, and then I see that I have 6 fluorine atoms. Fluorine has 7 valence electrons, just like chlorine. So I know fluorine is really only ever going to make one bond. It's a row 2 element, so it can't make beyond an octet. So I'm just going to give one bond to each fluorine, starting with each of the sulfur's valence electrons. And we're just going to do that for the lone pairs. So that's kind of it. That's how you draw these expanded octets. The tricky part is actually kind of spotting that you have one, because they aren't all as obvious as the 2 I started with. So you start by spotting them. Once you realize you have one that's going beyond an octet, then you just really leave the outer atoms alone, make the outer atoms normal. For example, chlorine and fluorine getting 1 bond each. And then the central atom is the one that has the expanded octet. Now, they get a little trickier if there's more lone pairs involved, but more or less that's kind of the same. So let's try the next one. If we do SF4, so this one might not obviously be an expanded octet, except for sulfur. Typically, we would expect it to make 2 bonds because it has 2 unpaired electrons. But I can see in this example, it's making 4 bonds because it's bonded to 4 fluorines. And so, again, just treat it like before. Every fluorine is going to take 1 electron to make 1 bond. So I just took 4 of those electrons, and I leave the other 2 alone as a lone pair on the central atom. And so that's the Lewis structure for SF4. Now I've got a polyatomic ion here that has an expanded octet. How do I know? Well, chlorine normally makes 1 bond. So again, I start with that central atom. I put all the dots here, and I expect it to make 1 bond. But I can see it's bonded to 3 oxygens, so it's clearly going to be making more than 1 bond, at least 3 bonds. Now, one approach I would say is that oxygen normally makes 2 bonds. So what I would probably do is give 2 electrons to every oxygen. In an expanded octet, one simplification is just give the outer electrons their normal number of bonds. So you can do that. Okay, we're not quite done though, because we've just used the normal number of electrons, and it should kind of rub you the wrong way that we have this unpaired electron left over. But if you recall, we have a minus charge, so that means there's an extra electron, and I'm going to use the extra electron to create a pair on the chlorine. So I end up with this, and to make sure I get the mark on a polyatomic ion, I add the brackets and I put the charge on the outside. Now, probably that might not be the best Lewis structure here, because as we'll find out soon enough with formal charge, I've kind of put the extra electron on chlorine, when really it would make a little more sense for the extra electrons to end up on oxygen, given that oxygen is more electronegative than chlorine. So another alternative here would be, instead of putting the all double bonds, some of them are going to have to double bond. But if I do at least one of the oxygens having a single bond, and so oxygen has 6 of its own, and if I take these 2 electrons that are here and I kind of do a coordinate covalent bond, so they share out to the oxygen like that, and then I do this just like I did before, give double bonds whenever I can to oxygen. And then I still have this extra electron that I'm going to add here to pair it up. And so this is an alternative structure. I still used the same number of electrons. It's basically like a resonant structure, if you will. The electrons from this double bond are moving out here, and so they're now they're there on the oxygen instead. So the oxygen is showing a little bit more ownership of the electrons in the second one, so the negative charge is kind of on the oxygen. In reality, it's kind of like a mix of the two. It's probably some sort of delocalization between the two. But I think both of these Lewis structures should probably earn a mark, although the one that I think is more likely to definitely earn a mark is probably this one. When there's a minus charge, it's probably going to be on the more electronegative element, if you can draw it that way. And this oxygen it kind of has a minus charge because it has like 7 valence electrons around itself. We're going to cover formal charge in our next video. But anyways, I digress. Let me get rid of those dots. For now, we're just trying to draw these structures, okay? So I think both of those are pretty good for right now. Other things that come up, if you try to do the 7 steps for these expanded octet examples, they won't work. They won't make any sense because the 7 steps tell you how to follow the octet rule, and these don't follow the octet rule. So if you did like SF4, for example, you'd say, well, I have 6 from sulfur, and I have 4 times 7 from fluorine, so I have 34 electrons. I need 40 electrons to feel like I have 40, and the difference is 6 electrons, which is 3 bonds. Well, there's no way that I can bond 4 fluorines to sulfur with only 3 bonds, because there's 4 fluorine atoms, so I need at least 4 bonds. So the 7 steps don't really make any sense when you have an expanded octet. Okay, there's a bunch for practice. Final thing I'll try to speed through here. These are the new electron domain geometries for VSEPR theory, and also the molecular geometries. Now, unfortunately, these get a lot more complicated than what we started with the 2, 3, and 4 domains. We just have to do our best to memorize them. They mostly focus on shape names, molecular geometry names, and they're less focused on bond angles, but we can do our best there just in case. So the 2 shapes that we get, we have 5 electron domains and 6 electron domains. The 5 electron domain shape is called trigonal bipyramidal. Now, it's a complicated sounding name. I like to think of the 5 shape as the 3 shape plus the 2 shape. So the 3 shape is trigonal planar, and the 2 shape is linear. And if I was to take the linear and sort of cut it right through the center of the trigonal plane, I would get this shape, which is trigonal bipyramidal. So here's the linear, and then here's the trigonal plane. So it's the 3 shape plus the 2 shape. That means I get all the angles of the 3 shape and the 2 shape plus 1 extra. So the angle on trigonal planar is 120, so I still get those around, I'm going to erase my stuff now. I still get 120 angles around that trigonal plane, those atoms. I also have a 180 angle between the top and the bottom atom. And then lastly, a new one. What's the angle between the trigonal plane and the linear? That's 90. So I end up with 3 different bond angles there. The other shape here is octahedral. Octahedral is really, it's called octahedral because if you made a shape out of it, or a 3-dimensional shape, it would be called an octahedron. It would have 8 faces. But really, when you have 6 things, it's actually a much simpler shape than the 5 one. It's just like an XYZ or an XYZ set of axes. So they're all perpendicular to each other. They're all 90-degree angles from each other. And the name of that is called octahedral. So you have these 2 kind of key main shapes and their key angles. And then we're going to create different shapes when there are lone pairs on the central atom. So starting off with the trigonal bipyramidal, when you add the lone pairs, you think of them adding to the sort of trigonal plane part of this shape. So you have the linear part here. That's going to kind of stay intact. And we're going to, one by one, take off atoms and replace them with lone pairs on the trigonal plane. So I start here with a lone pair. And what's left is the shape that they call seesaw. If you take off 2, you're left with a shape that they call T-shaped. And if you take off 3, strangely enough, you're actually back to linear, because remember, it's a 3 shape plus a 2 shape. So if you take away all 3 of the trigonal planars, you are left with just 2 up and down, and that is linear again. If you're doing angles, then we can apply our rule that initially this is like a 120 angle, and so this lone pair is going to shrink that angle down to roughly 117. It probably pushes these ones a little bit closer together than 180, maybe 177, for example. So we can still just use that same general rule to get a rough approximation of the angles. I'm not going to go beyond that here for the sake of time. And then if we look at the 6 electron domain shapes, again, starting with the octahedral, in this one, they are sort of all equally spaced, so we could really think of removing any of them, but it's a bit easiest to picture if I remove this bottom one first and replace it with a lone pair. So if I do that, I end up with a square pyramid, has a square base, and they all kind of point up to this top one. So we call it square pyramidal. And then if we take away 2 lone pairs, they're going to add as far away from each other as possible. Since those lone pairs have the greatest amount of repulsion, they should always be adding on opposite sides, and we end up with this shape, which is called square planar. So the octahedral one is really like square based, right? It's kind of this central square, and then you've got really like 2 square pyramids at first. Sometimes you see this called square bipyramidal. So you have these 2 pyramids coming out of that plane, then you just have the 1 pyramid coming out of that plane, and then you just have the square plane. Anyways, I know it's a lot more to remember. We practice and we do our best. These are the molecular geometries for the expanded octets.